Hello and welcome to this Eureka on the topic of industry discussion. My name is Paul Fanning and I'm editor of Eureka. Today our topic is exoskeletons, their development and use across a number of sectors. And here to discuss this with me today is Matt Dean, sales engineer at Maxon. Now Maxon has worked extensively in this area for some time, but for those less familiar with the topic, perhaps you could start by giving us a brief history of exoskeleton technology.
Yeah. Hi, Paul. Okay, so exoskeletons are not new devices. They've been around for hundreds of years, but the bit that we're interested in at Maxon is the active exoskeleton, not the passive type. Active implies it's powered, and very early attempts of powered exoskeletons came about maybe 100 or so years ago in Russia, of all places. They tried a gas-powered exoskeleton. I think it was more just an exercise in engineering to see what was possible. Then a little bit later, just towards the end of the First World War, the US developed a exoskeleton. This time it was steam powered, and I don't think we need to discuss too much the downsides of that.
No.
It wasn't really until the 1960s that sort of serious, realistic exoskeletons, active exoskeletons, became a sort of reality. Reality is I'm using the word loosely here, Paul.
I suppose they're sort of associated in the public mind to some extent with sci-fi. But what was the background to that development?
It was military, so it was developed by GE and the US Army, and I think they wanted to make like a super soldier, shall we say?
Yep.
They developed a suit that did that, and it increased the strength of the soldier, or the power of the soldier maybe, by a factor of 25, which is significant. There was a downside to this.
I can imagine, yeah.
And the weight of the exoskeleton was 0.7 of a ton. So soldiers need to be mobile, and power supplies, battery packs just didn't enable it to go anywhere. But it did demonstrate the thinking behind trying to do something along the lines of the military. The first medical sort of example is a similar time in Eastern Europe in Yugoslavia. A professor worked on a suit to help paraplegics using compressed air to aid movement, but again ran up against limitations of control, power, size. I think it did help patients, but not in a way that we would understand it as being a success. But it did show the two sort of streams early on as to the way people were thinking, military and medical. The person who really sort of had a proper go and put in all the components together with some success was a gentleman called Monty Reed, who was a paratrooper, and in an accident he broke his back, and he decided, okay, an exoskeleton is something he needed, so he started developing one in the 1980s, and by let's say 2005, he actually walked 3 miles with his device. I think it was the 12th or 13th prototype on the Seattle St. Patrick's Day Dash, it was called, and the average speed of 2.5 miles an hour. But he did it, and that's the first person who sort of put all the components togetthat and got something that actually aided him. So that's really where we are.
Okay, so that brings us up to the present day. So where is the where is the technology now? And what sort of applications are they being used in, or can they be used in now?
So exoskeletons today, there's four main streams of thought. The two that we've covered, military and medical. Medical is the main focus for Maxon. We'll come on to a little bit of that later. So military, medical, industrial. So imagine in an assembly plant building cars or lifting heavy objects in a repetitive type operation to aid production, and also in civilian use. So it could be firefighters, rescue workers, where they might be carrying a lot of equipment or maybe carrying someone. So they're the sort of four main areas. But as I said, the main focus for Maxon is in the medical area.
So how did that start for Maxon? What was the story there?
Well, the story there, it really started with the development of, I call it the flat motor. So this is an example of it here. So this is 90 mil in diameter. So at Maxon, we have a family of these ranging from just under 10 mil up to this one, which is 90 mil. And the key thing with this motor is, as the name suggests, it's flat. Big diameter, flat, and the rotor, you've got the magnet running around just the inside of the rotor. And what this type of motor gives you is it gives you large amounts of torque. You don't need huge speed, talking, I don't know, 5, 6, 7,000 RPM, that sort of speed on the output here. But it delivers torque. And, excuse me, torque is one of the major things that people need when developing a robotic joint or an exoskeleton joint. So with the development of this type of motor technology, coupled with gearboxes, feedback devices, encoders, relative or absolute, and the electronics to control the motors, you had the basic building blocks to build an exoskeleton joint. So that's, if you go back 15 years, that's where Maxon was. And what people were doing is, universities we were working with and other research establishments, people were putting these components together to build up a joint. And what you quickly realize is that you're fighting weight and space. You don't have the luxury of space, if you're carrying it around on your body, to start bolting bits together to make joints. So an exercise was carried out at Maxon where the sort of general themes of what was required by these joints started to come together. And dedicated products were launched in order to stop people developing their own joints and actually give them an assembled joint. Nice. I can show you an example of this type of product. So I'm sharing my screen here. And what I'm sharing there is this here, what I'm holding up in my hand. This is a joint that has everything inside it you need to power a joint on an exoskeleton. And this is the exploded view. And what you can see here is, if you look at the rotor turning inside the motor, traditionally the motor would be built onto a gearbox. But in this type of device, what we've actually done is start building the gearbox components actually inside the motor. So again, you're saving weight and you're saving size, which is absolutely critical. But from a device like this, we're able to deliver up to 140 Newton meters at the output of it. And the whole idea is the power density needs to be as high as possible.
And the weight as low as possible.
Exactly, the weight as low as possible. And also the communication links here with EtherCAT, very fast communication links. So the whole thing comes together as a package so that people no longer need to develop their own joints. They can get what they need as a product.
Yeah, I see. So it's in a sense almost an off-the-shelf. It's an off-the-shelf solution virtually in that sense.
Virtually, yeah. I mean, it can be modified to suit individual needs, but that's the concept that we've moved to, Paul, away from supplying components. We're now supplying the complete system.
Okay. And I mean, are there any other engineering challenges that these technologies pose that we haven't already touched on?
Yeah, I mean, if we look at let's take the motor. So the motor part is the top part of this slide here. So here you can see the rotor and the stator. We've made the rotor as big a diameter as we can, but also hollow. So the inertia is low. And the green part around the winding, a traditional winding, when you look at it, looks like this. You can see the copper wire. On this type of motor inside the joint, we've actually potted it with a heat conducting material, so that from a given size we can get as much power in there as possible, and we can get the heat out as quickly as possible. That's one of the big pluses of this type of motor. The other products that we've developed, you can see there's an encoder there. Traditionally, encoders would be bolted onto the back of motors. With this type of motor, that isn't possible because you don't have a shaft running through it. So we've developed encoders that run on a rotating magnet, which can be put onto the rotor that you can see in the motor above.
Yeah.
Another key part of the development of the joint is, okay, I've talked a little bit about the motor, but the motor is half of it. The other half is the power transmission side, or the gearing side. And the big enemy on this type of an exoskeleton joint or a robotic joint is backlash in the powertrain or the transmission train. And we've developed a type of gearbox which is able to deliver very high levels of torque, but has very low backlash in it. We call it the Cyclo Flex Wave gearbox. And the other thing which is key with it is it's very short, big diameter or similar diameter to the motor, but very flat.
Okay. Yeah.
And also, you also need, you might have two types of feedback in the device. One, the controller will be talking to the motor, so it needs to know the position of the rotor of the motor, but also you need to know the output position of the joint. So you'll have two elements of feedback going into the controller. So we have an absolute encoder that we use, and we can mount that onto the output. And we also have an encoder that we can use to commutate the motor on the other side. So yeah, more feedback, which we've developed.
Well, I mean, it seems an obvious thing to say in one sense, but of course, the challenge is posed by the fact that this is a piece of technology that has to be worn by a human being. It has to be always in your head at any given time when working on it, I guess.
Yes, and if you think of if you just take your arm, for instance, you know, if it's pivoted here, if you make something heavy and put it on the end of your arm and you hold your arm out like this, you've got a big lever here. Yeah. You know, so the further away from the center of core of your body you get, you really, you know, every gram needs to be worried about. Yeah.
Well, fascinating. Okay. So, I mean, this is where we are, but where does Maxon see the greatest potential for adoption of exoskeleton technology, and, you know, looking to the future now?
Okay, so there's Maxon's heavily involved in it's called Cyclothon, which is a type of it's a competition, a worldwide competition like the Olympics for wearers of exoskeleton type devices. Cyberthon it's based in Zurich, but they hold the event all around the world, where they set up hubs around the world where people can go to the hubs with their devices, and the users they put through a set standard of tasks, a set series of tasks. It could be there'll be a simulated train carriage, with the seats on the train carriage, and the exoskeleton user gets on and has to maneuver themselves into a train seat, or walk along over some uneven shaped boxes, so the stride has to change, and also the height would change as well. Things that we take for granted, but from a user of an exoskeleton are significant challenges. The Cyberthon events held usually in February, and they have entrants from all over the world, where the patients and the research people and the universities are all coming together to push forward this type of technology. Nearly a third of them are all using our products. And as I said, Maxon is a major sponsor of the event. So we're heavily involved in supporting the development of exoskeletons in the medical sector. The key aim, I'll just roll my slide on here. This here you can see inside a device that was used at an event at the Cyberthon. What they've done, if you look at the top of the joint, they've actually separated the motor and the gearing. They've actually run it in parallel, connected it with a belt to try and reduce the overall width of it. But this is the type of product that is being tested at the event. And I think the main goal here with all this is to replace the wheelchair. I mean, the wheelchair is, it enables many people to be mobile and whatnot, but there is, you are sat down, which brings with it other health problems, and being able to mimic walking, at the right height and the right speed, and able to go up a few steps and all the rest of it is a real big plus. So we're not there yet. There's still work being done, but it's through competitions like the Cyberthon and the advancement in technology and these types of products that we'll get there one day. Fantastic.
And where could people go to find out a little bit more about this kind of thing?
Well, the obvious place is the Maxon website. If you type Maxon UK or just Maxon into your browser, pretty near the top you'll come up with Maxon's homepages, and there's lots of stories in there about these types of events and our type of products. Or obviously just contact Maxon. We're here, and we're usually engineers, and very keen to help. Brilliant.
I mean, it's been absolutely fascinating. Thank you so much for your time today, Matt, and I'm sure everybody out there would join me in saying in that thank you. But unfortunately, that's all we have time for. But as I say, thank you very much, and thank you very much for joining us.
Thanks, Paul. Bye, everyone. Bye.
Bye.